Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering.
Welcome to part 3 of the fundamentals of VLSI chip physical design. In this part, we will explore the key topics like fundamentals of signal integrity, power dissipation, thermal characteristics, and reliability. These closely related topics play a vital role in ensuring correct operation and long-term chip performance. So, let's get started. Signal integrity refers to the ability of a signal to travel through an integrated circuit while preserving its intended voltage, timing, and waveform. As VLSI technology continues to scale, chips operate at higher speeds with billions of closely packed transistors. This increases electrical interference caused by switching activity and interconnect parasitics. If not properly controlled, these effects can distort signals and lead to timing and functional errors. In this section, we will explore the major signal integrity challenges, their impact on chip performance, and the design techniques used to minimize them. Signal integrity issues arise whenever the transmitted signal no longer reaches its destination with the required voltage level, timing, or waveform. As chip complexity and operating speeds continue to increase, maintaining signal quality becomes increasingly challenging. These issues originate from several electrical and physical factors present throughout the chip and can adversely affect circuit operation. Their effects include incorrect logic interpretation, timing degradation, and reduced circuit robustness. In the following slides, we will examine each of these causes and their impact in greater detail. As semiconductor technology scales, adjacent metal interconnects are placed increasingly closer together, creating unintended electrical coupling between neighboring signal lines. This coupling occurs through parasitic capacitance and mutual inductance naturally present between the interconnects. The actively switching signal line is called the aggressor, while the adjacent line receiving the unwanted coupled signal is known as the victim. The strength of this coupling depends on factors such as interconnect spacing, parallel routing length, and signal transition speed. Understanding the aggressor-victim relationship forms the foundation for analyzing crosstalk, noise, and timing degradation in high-speed VLSI designs. Interconnect coupling gives rise to several signal integrity issues that can affect the reliable operation of a VLSI chip. The most common of these are crosstalk, noise, glitches, and signal reflections, each influencing circuit behavior in a different way. Some primarily affect signal voltage levels, while others introduce timing errors or waveform distortion. The severity of these issues increases with higher operating speeds and shrinking technology nodes. Further signal integrity issues are ringing, ground bounce, simultaneous switching noise, clock jitter, and clock skew primarily affect signal stability, clock synchronization, and timing accuracy. These effects become more pronounced as switching speeds increase and larger numbers of circuits operate simultaneously. If not properly controlled, they can reduce timing margins and degrade overall chip performance. These waveforms illustrate how common signal integrity issues appear on actual signals during high-speed operation. Instead of ideal square wave transitions, parasitic effects distort the waveform through crosstalk, ringing, reflections, and overshoot or undershoot. Such distortions can alter voltage levels, increase propagation delay, and reduce the available noise margin. The severity of these waveform abnormalities depends on interconnect characteristics, switching speed, and circuit loading. The strength of capacitive coupling between adjacent interconnects depends not only on their spacing but also on the direction in which the two signals switch. This behavior is represented by the Miller coupling factor, which determines the effective coupling capacitance seen by the aggressor and victim nets. When both nets switch in the same direction, coupling is minimized, whereas switching in opposite directions produces the maximum coupling effect. As technology scales and interconnect spacing decreases, the influence of the Miller coupling factor becomes increasingly significant. Understanding this relationship helps physical designers predict cross-talk effects and optimize routing for improved signal integrity. Capacitive coupling between adjacent interconnects transfers a small amount of switching energy from the aggressor net to the neighboring victim net. This transferred energy appears as a short-duration voltage disturbance, commonly referred to as cross-talk noise or a glitch. The polarity and magnitude of the induced pulse depend on the aggressor's switching direction, transition speed, coupling capacitance, and the electrical characteristics of the victim net. If the induced glitch exceeds the available noise margin, it may be interpreted as a valid logic transition, resulting in false switching or timing violations. Preventing such unwanted glitches is therefore an important objective of signal integrity, aware physical design. The effect of crosstalk can appear in several forms, depending on the direction and speed of signal transitions on the aggressor net. These waveform distortions include overshoot, undershoot, rise glitches, and fall glitches, each affecting the victim signal differently. While some distortions briefly exceed the normal voltage limits, others produce unwanted positive or negative logic pulses. The type and severity of the disturbance depend on factors such as transition direction, coupling strength, and interconnect characteristics. Identifying these different cross-talk effects enables designers to evaluate their impact on circuit operation and apply suitable mitigation techniques. Not every crosstalk-induced noise pulse results in a functional error, its impact depends on the receiver's available noise margin. The magnitude of the induced voltage is influenced by factors such as coupling capacitance, aggressor voltage swing, switching speed, victim impedance, and driver strength. If the induced noise remains below the receiver's threshold, the signal is correctly interpreted and normal operation continues. However, when the noise exceeds the available noise margin, the receiver may incorrectly detect a logic transition, resulting in false switching, timing violations, or metastability. Maintaining adequate noise margins is therefore essential for ensuring reliable signal transmission in high-speed VLSI circuits. Signal integrity issues cannot be eliminated completely, but they can be effectively controlled through careful physical design. Designers reduce cross-talk, reflections, ringing, and clock-related disturbances by optimizing interconnect routing, spacing, shielding, buffering, and clock distribution. Maintaining a robust power distribution network and controlling signal transition times further improve circuit stability. These techniques preserve signal quality, increase timing margins, and minimize functional errors during high-speed operation. Ultimately, successful signal integrity design ensures that every signal reaches its destination accurately, reliably, and at the intended time. Signal integrity is significantly improved through careful interconnect layout during physical design. Shielding isolates sensitive signal lines from electrical interference, while increased spacing reduces capacitive coupling between adjacent nets. Routing signals on different metal layers and avoiding long parallel runs further minimize both capacitive and inductive coupling. Buffer insertion restores signal strength, breaks long coupling paths, and reduces propagation delay. Together, these layout optimization techniques improve signal quality, increase timing margins, and ensure reliable operation of high-speed VLSI circuits. Having explored signal integrity, let us now examine the sources of power dissipation in CMOS logic gates. During logic switching, Energy is consumed in charging and discharging the load and parasitic capacitances, producing dynamic power. A small amount of short-circuit power is dissipated while both the PMOS and NMOS transistors conduct simultaneously during signal transitions, and static leakage power results from small leakage currents that continue to flow even when the gate is not switching. The total power consumed by millions of such logic gates determines the overall power dissipation of a VLSI chip. In the following slides, we will examine how these power components collectively contribute to the chip's total power consumption. Power dissipation in a VLSI chip is not limited to the logic gates alone. The passive physical elements of the chip also contribute significantly. Signal interconnects, power distribution networks, metal layers, vias, contacts, and their inherent parasitic resistance, capacitance, and inductance consume power during signal and power transmission. These passive elements introduce charging and discharging losses, IR drop, Joule heating, propagation delay, and transient voltage effects. As technology scales and interconnect density increases, their contribution to overall chip power and performance becomes increasingly important. Optimizing the physical interconnect structure is therefore essential for achieving low power, high performance, and reliable VLSI designs. Active circuit elements perform the functional operations of an ASIC and account for a major share of the total chip power consumption. Logic gates, flip-flops, memories, clock circuits, digital macros, analog blocks, and I/O interfaces consume power while processing, storing, and transferring data. Their power consumption arises from continuous switching activity, clock operation, internal bias currents, and the need to drive large on-chip and off-chip loads. Large functional macros including SRAMs, processors, PLLs, ADCs, DACs, analog circuits, and I/O interfaces typically account for approximately 60 to 80% of the total chip power, while the remaining power is consumed by standard cell logic, clock distribution, and interconnect networks. The exact distribution depends on the ASIC architecture and application. Power-aware circuit architecture, clock gating, power gating, and voltage optimization are therefore essential for achieving high performance and energy-efficient VLSI designs. The power consumed by a CMOS logic gate depends not only on its internal design but also on the conditions under which it operates. Parameters such as supply voltage, switching frequency, input transition time, output load capacitance, transistor dimensions, operating temperature, and process variations directly influence the total gate power. These factors determine the relative contribution of dynamic, short circuit, and leakage power during circuit operation. To ensure accurate chip-level power estimation, every standard cell is pre-characterized over different process, voltage, and temperature, or PVT, conditions. These power models enable EDA tools to predict power consumption and support power-aware optimization throughout the physical design flow. The total power of a modern VLSI chip is distributed across several functional and physical elements rather than being concentrated in the logic gates alone. Clock distribution networks, memory macros, core logic, large functional blocks, interconnects, and I/O interfaces each contribute a significant share of the overall power budget. The exact distribution depends on the chip architecture, application, operating frequency, and technology node. Large macros and clock networks often dominate power consumption and strongly influence routing congestion, thermal hotspots, and overall chip performance. Understanding where chip power is consumed enables designers to optimize power, timing, thermal behavior, and reliability throughout the physical design process. Power integrity, signal integrity, and the clock tree are closely interconnected and must be optimized together to achieve a robust VLSI design. Variations in supply voltage, interconnect resistance, capacitance, inductance, routing, and temperature simultaneously influence power delivery, signal quality, and clock distribution. A weakness in any one of these areas can lead to timing violations, increased power consumption, signal degradation, and reduced chip reliability. Physical designers therefore analyze these parameters relationships as shown in the table and, combinedly achieve balanced performance, power efficiency, and timing closure. We will now examine how the power dissipated within the chip is converted into heat and how thermal effects influence long-term reliability. Once the silicon die is fabricated, it is mounted inside a package that provides the mechanical, electrical, and thermal interface between the chip and the external system. The die I/O pads are wire bonded to the package leads. The package protects the die from mechanical and environmental damage. Besides carrying power and signals, the package also provides the primary path for removing the heat generated within the chip. The choice of packaging technology influences electrical parasitics, thermal resistance, power delivery capability, and high-speed performance. A well-designed low thermal resistance package is therefore essential for achieving efficient cooling, reliable operation, and long-term ASIC performance. The heat generated within the silicon chip must travel through the package before it is finally dissipated into the surrounding ambient environment. This heat flow is characterized by a series of thermal resistances, representing the resistance to heat transfer from the junction to ambient through the package, the heat sink, and ultimately the ambient air. Lower thermal resistance provides a more efficient cooling path, resulting in a lower junction temperature and improved chip performance. Thermal resistance depends on the package material, die attach, thermal interface material, heat sink shape and area, and cooling mechanism. This thermal model enables designers to select appropriate packaging and cooling solutions to ensure safe and reliable ASIC operation. A high-performance ASIC is valuable only if it continues to operate correctly throughout its intended service life. Reliability ensures that the chip maintains its electrical, timing, and functional characteristics despite continuous operation and exposure to electrical, thermal, and environmental stresses. As semiconductor devices age, gradual changes in transistors and interconnects can reduce performance and increase the probability of failure. Modern VLSI design therefore considers reliability from the earliest design stages alongside power, performance, and area optimization. In the following slides, we will examine how device aging occurs and the techniques used to evaluate and improve long-term chip reliability. Every semiconductor device undergoes gradual aging as it operates over months and years under electrical, thermal, and environmental stress. These aging mechanisms slowly alter the characteristics of transistors and interconnects, affecting switching speed, leakage current, propagation delay, and overall circuit performance. Higher operating temperature, supply voltage, switching activity, and current density accelerate this degradation process and shorten the expected chip lifetime. Through careful thermal management, optimized power distribution, and reliability-aware physical design, designers can significantly slow the aging rate. The objective is to ensure that the ASIC continues to meet its specified performance and functional requirements throughout its intended operating life. The product reliability and life testing of an ASIC under real-time evaluation is a highly time-consuming process. Since real-time evaluation is time-consuming, statistical accelerated batch testing is carried out on sampling batch basis. This methodology evaluates devices at accelerated temperatures, voltages, humidity, and electrical stress and simulate long-term storage and switching life operation, within a much shorter time. These tests reveal early life failures, wear-out mechanisms, and performance degradation before the product reaches the customer. The measured results help engineers validate the chip's electrical, thermal, timing, and functional robustness throughout its intended service life. Reliability evaluation and certification by batch acceptance tests provides to the customer the confidence of ASIC product lifetime operation under real-time field operating conditions. Reliability requirements are not the same for different ASIC market segments like consumer, industrial, defense, and so on. It depends on the application and the operating environment. Consumer products typically prioritize low cost and moderate lifetime, while industrial, defense, and space systems demand much higher reliability under wider temperature ranges and harsher environmental conditions. As the application becomes more critical, tighter electrical specifications, longer operational life, and lower acceptable failure rates are required. These requirements directly influence the chip architecture, package selection, qualification testing, and manufacturing standards. Defining the target application at the beginning of the design cycle is therefore essential for developing an ASIC that meets its intended performance and reliability objectives. A typical ASIC acceptance conditions for different market segments is shown in the table. Building a reliable ASIC requires much more than functional correctness. It demands the careful integration of signal integrity, power integrity, thermal management, and reliability throughout the design process. Optimized physical design, efficient power distribution, controlled operating temperatures, and robust verification together ensure stable chip operation over its entire lifetime. Every design decision, from floor planning and routing to clock distribution and package selection, contributes to the final product quality. Comprehensive design validation and reliability evaluation provide confidence before the chip enters production. Ultimately, the objective is to deliver an ASIC that consistently meets the customer's functionality, power, thermal, and reliability requirements throughout its intended service life. With this, we conclude Part 3 and complete our journey through the fundamentals of VLSI chip physical design. Across these 3 presentations, we explored the physical structure of a chip, timing fundamentals, signal integrity, power dissipation, thermal management, and reliability, the key concepts that govern modern ASIC design. While industrial design flows involve many advanced tools and methodologies, a strong understanding of these fundamentals provides the foundation for learning them effectively. We hope this series has given you a conceptual understanding of the physical design challenges involved in building high-performance and reliable VLSI chips. Thanks for your time, and hope to meet you in the upcoming video. Bye for now.